I will be giving a demo of how we use the PMI software in the analysis of LC-MS data from X-ray footprinting experiments. We'll be looking at data from the X-ray radiolysis of samples containing cytochrome C, which was the protein used to test the JET sample delivery system at the ALS footprinting beamline. Before I start the demo, I would like to give a brief overview of the two workflows we use in Byos. The data analysis process I'm sharing with you today has worked well for us, but I should point out that there are several ways of working with in silico peptides in Byos. In the cytochrome C example, we're analyzing one moderate exposure MS2 file in the oxidative footprinting workflow, which is where the identified modifications are scored and validated prior to the creation of an in silico peptide library. After the creation of the in silico CSV file based on MS2 data, the in silico file is then applied to several cytochrome C samples in the PTM in silico workflow for which mass spec data was acquired in MS1 mode. This combination of MS2 and MS1 data ensures that we can identify residue-specific oxidative modifications while at the same time achieve good data quality. The final step of the analysis involves the creation of dose-response plots in Excel, from which we derive the rate constants. So let's take a look at the data. Here we have the overview of the Byos workflows, and we're going to go ahead and select the oxidative footprinting workflow. And I will launch a workflow that's already been set up for cytochrome C. The workflows consist of three tabs: the Samples tab, the Sequences tab, and the Processing Nodes tab. In the Samples tab, you'll be bringing in the mass spec files that you'll be working with. And then in the Sequences tab, you'll bring in the FASTA file for the protein or proteins of interest for your project. And then in the Processing Nodes, there are several parameters and settings, and I'm not going to go over all of them in the demo today. I just want to highlight a few. One is for the digestion. Right here we have specified a trypsin digest, and we're allowing for 2 miscleavages. And then in terms of the modifications, we have specified fixed and variable modifications that are appropriate for an oxidative footprinting workflow. And then once you are satisfied with your parameters, you will go ahead and click the button down here, Create Project, and that will start the project creation. Once the project has been created, you will get a report with several tabs. And one of the first is the PTM summary tab, which first of all shows you the degree of sequence coverage. In this case, we're at about 80%. And then it also gives a really nice global view of the degree of oxidative modifications that have been identified for the peptides that have been picked up in this particular analysis. In the peptides table of the project, we have access to all the peptides identified from the MS data, both native and modified peptides. When you select a peptide with a modification, you will see the associated native peptide down here in the wild type peptides table. And further down, we have the extracted ion chromatogram plots. The top panel shows the XIC for the modified peptide, and the bottom panel shows the XIC for the native peptide. Over here to the right, we have the MS2 fragment ion spectra, and you can also view that data in a table view format, which is very helpful. And then finally here in the bottom right part of the screen, we have the associated isotope plots. In terms of validation, what I like to do first is to take a look at the scores and the delta mod scores across the entire data set. I'd like to just kind of go through and get a feel for how good the data quality is as reflected in the scores. Another thing that's really helpful is the ability to filter the data based on filters set for specific columns. For example, if we're interested in looking closer at the scores, we could go ahead and filter for peptides scoring, for example, below 200. So we have a few peptides here that are scoring on the lower end, and it's really nice just to have the ability to focus on, for example, low-scoring peptides that might require a bit more attention in terms of validation. And once you've used that filter, you can go ahead and remove it or apply other filters. Another feature we look at as part of the validation process is the retention time of the modified peptide versus the retention time of the native peptide. And we typically see a negative peak shift for peptides with an oxidation modification. So that's another good high-level check as part of the validation process to make sure you're actually seeing that expected shift in retention time. If we take a look at a couple of the modifications in this particular data set, we have a peptide right here that has two modifications, a tyrosine modification and a methionine modification. And what actually happened when this project was originally created, this was reported as a mixed modification, meaning that the XIC area included all the peaks shown here, basically encompassing both modifications. I took a look at the retention times for the tyrosine modification. We have two peptides associated with that modification, and then for the methionine modification, we also have two peptides. And it so happens that the two tyrosine modifications are associated with the two peaks right here, whereas the two peptides with the methionine modification are associated with a peak right here. So I went ahead and split the XIC area into two areas that are more appropriate for the tyrosine and methionine modification. If you have a situation where your retention times overlap in terms of a peptide that has multiple modifications, you can just go ahead and report that peptide as a mixed modification peptide. Let's look at another peptide modification. Here we have a small peptide with a lysine modification, and 3 peptides were identified for this particular modification. The first 2 peptides are associated with the first peak right here. However, the third peptide has a retention time that puts it in the second peak here, which is a little suspicious. If we look at the fragment ions that were identified for the third peptide, we see that we don't have great coverage for the glutamine and the lysine residue. And we can also take a look at that in the table format. As a result, I went ahead and labeled that particular peptide as uncertain using the validate column here. In this column, we have 4 choices. We can leave the modification as unassigned, true positive, false positive, or uncertain. Since we have this third peptide labeled as uncertain, we're also going to go ahead and adjust the XIC area so that we end up with a more appropriate XIC area for the 2 remaining peptides with the lysine modification that we have labeled as true positive. Once you're satisfied with the manual validation, you can go ahead and set the peptide filter that will be used to generate the in silico CSV file. Here I've set the minimum score to 200, and we want to make sure we deselect the peptides that have been labeled false positive and uncertain. since we don't want those included in the CSV file. And then we'll go ahead and click OK. And after that filter has been applied, we can see that in our validate column, we're left with peptides that are either unassigned or those that have been labeled as true positive peptides. So at this point, we can go ahead and generate the in silico peptide library, and we do that by going to the Edit menu and in silico peptides, and then we export in silico to CSV. Once the in silico CSV has been created, we can go ahead and launch the PTM Pure in silico workflow. Here in the Samples tab, we have the MS1 files that we're going to apply the in silico CSV to. And then in the Sequences tab, we have the same FASTA file for our protein of interest that we used in the oxidative footprinting workflow. And in Actionable Nodes, we're going to go into in silico options and make sure that for the in silico peptide CSV that we are pointing to the CSV file that we just created. And once that has been set up, you would go ahead and create the project. And so here we have the result of the pure in silico PTM workflow. We have our 5 MS1 samples, and we can see here we have that nice global view of the peptides that have been identified with the associated modifications. And then if we go to the second tab, we have a pivot table with all 5 samples listed here in the top row, and they are listed in order of increasing exposure time. And then in terms of the column fields that have been brought in, we have the type of modification here. It's dioxidation and oxidation, and we are also looking at the specific residue modification in terms of the position number and the amino acid that has been modified. And if we could just kind of quickly take a look at the data here, we see a general trend that as the exposure time increases, we see an increase in oxidation as expected. At this point, we could look at a couple of specific peptides. What I did is that I made a copy of this tab, percent mod by mod name across samples. I went ahead and make a copy of that tab here. And then I selected for 2 specific peptides. One has a tyrosine modification, the other one has a methionine modification. And these are the 2 peptides and the 2 modifications we're going to use to create dose response plots in Excel for this demo. And I just wanted to show that you have a lot of flexibility with these these pivot tables in terms of bringing in the column fields that you're interested in. So what I did here, I brought in the sequence and I selected for the 2 peptides that I'm interested in. And that's how I was able to narrow it down just to these 2 modifications. And so the data we have here is the percent modification for various exposure times for just these 2 modifications. From here, we can go ahead and export this data to Excel, and we do that as an export pivot table content CSV. Once you export the pivot table content to Excel, you end up with a CSV file that looks like this. And I took the data and I transposed it into a format that's a little bit more conducive to generating dose response plots. So we have the original percent modification figures here for the tyrosine 97 and methionine 65 modification. And I went ahead and calculated a fraction unmodified on the basis of those figures. And I also normalized the data for the methionine modification, since we do have a little bit more than 2% background oxidation for methionine. The normalization of the data basically ensures that the dose response plots are reflective of just oxidation related to footprinting and not background oxidation. And so once you have your fraction unmodified data calculated, you can go ahead and plot fraction unmodified as a function of exposure time. And on the basis of that plot, we can go ahead and generate a trend line. This is a single exponential fit. So we have one here for each residue, along with the associated trend line equation and the correlation coefficient. From the equation, we can derive the hydroxyl radical reactivity rate constant, and I've shown that down here for both residues. And the rate constant is a measure of both the intrinsic reactivity and the solvent accessibility for that particular residue. That's all I have today. Thanks for listening, and please let us know if you have any questions. Thanks.